Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. Welcome to the course on comprehensive view of speech processing. So, today's lecture is the 7th lecture in its series. So, today we are going to discuss on acoustic phonetic representation of speech sounds, and we are continuing this topic for the last two lectures. In the last two lectures we discussed about this acoustic phonetic representation of speech sounds in the context of a complete sentences and vowels. So, today we will continue that is acoustic phonetic representation of vowels. We will start with that topic. Yeah. So, from this picture it is you can able to see that there are different subfigures in this slide. So, each of them corresponds to the articulation of different sound units. So, if you look at here on each subfigure, so there is a vowel uttered, and how that the context of that vowel, that means how that vowel in the context of uttering a particular word, how that vowel is uttered. So, in uttering that word, in the uttering that particular vowel, how what will be the position of the tongue hump and the nature of the tongue hump, that is the height of the tongue hump. So, if you look at here, like you can see this corner, this particular figure corresponds to the position of tongue hump when you are uttering the vowel e in the context of eve. In the context of eve, you can able to see that the tongue hump at the frontal position, right? And whereas in the context of for the vowel, for the word it, you can see the tongue hump is somewhat lowered, and but still the tongue hump is at the frontal position. So, that way if you look at here, this is hate, it means here when you are uttering the vowel a, you can able to see how the tongue position, the tongue hump position. And similarly in case of met, and likewise for uttering the different vowels, you can see for the uttering the vowel a, for example, in the context of father, or where you can see a tongue hump at the back position, right. Similarly all. So, you can able to see there are variations in the vowel, and those things, those variations of the vowel, you can able to observe in English language. When you are uttering the various words, you can encounter, you can able to perceive the variation or different types of vowels at all. You may not perceive these vowels in the context of the other languages, such as for example in Indian languages, you may not able to perceive, or you may not encounter all the vowels whatever that are presented over here and all, right. And here then, so these are the, like you can see there are like 10 different waveforms that were shown here, and these are corresponds to the different vowels. The top two waveforms corresponds to the vowel e, short e and longer e, and then a, the next two waveforms, and then the o and a and then u. Likewise, you can see that here the waveforms are plotted starting from the tongue hump at the front position, and then the bottommost waveforms corresponds to a tongue hump you can able to see at the back position, or tongue hump at the back position. And accordingly even in the time domain waveforms also, but for all of them, since they are vowels, you can able to see the periodic structure, a kind of a periodic structure across all the waveforms. But there are variations because the waveforms corresponds to 10 different vowels. So, therefore, each of them have some distinct pattern. A commonality is that all of them have a periodic in nature because they are uttered by maybe the same speaker. So, since since all the way vowels are uttered by same speaker, so because of the same excitation mechanism offered by the same speaker, so the periodicity is more or less similar. But you can see that for different vowels, for the distinction between one vowel to other vowel, you can able to see in each waveform is unique, you can different. You can see in case of E, where there is a low frequency content as per the periodicity offered by the vocal folds excitation, and on top of that you can able to see there is a random noisy structure. So, this corresponds to, this can be contributed to the frequency content at a high frequency range, or you can say that the energy contribution or concentration at a high frequency range. Whereas, when you come to the A and all, where you can see that the effect of this noise is less. So, but there is here you can able to see there are also more oscillations compared to the previous signal. So, therefore, here you can able to see these 2-3 waveforms, they contributed to well defined the formant structure. It means the energy was concentrated at 3 or 4 different frequencies. Then when you come to the last, the bottom waveforms, where they corresponds to back vowel, you can see that almost like here these waveforms are like they are free from this noise whatever you observe at the waveforms at the top. So, therefore, when you see the spectrogram here, most of the energy is focused or concentrated at a very low frequency. And again, if you look at a very last waveform, the bottommost waveform, it corresponds U, but again this was uttered in some other vowel configuration O. So, therefore, you can see again here there is some noisy structure that was superimposed on this low frequency content. So, you can able to see the more detailed characteristics of the frequency components or energy that is associated to various frequency components in the form of spectrograms. So, here you can see there are 10 different vowels and their spectrograms were shown over here, and here the first here these spectrograms are ordered as per the time domain signals that were shown in the previous slide. So, here can say this is the E and this is E, A, and then so on different vowels, and here this corresponds to A and O, then U, then U, then U. So, if you look at here, you can able to see more distinction or more unique characteristics in the spectrogram, where in case of E you can see that the first format is lower one, and then second format is very high, it's above almost like 2000 hertz. And similarly in case of E, where the initial portion of the short vowel and a long vowel, they are found to be similar, but when you after some time in case of long vowel, where you can able to see that the second format is coming close to the first format. And likewise for different vowels like A and A, you can able to see that there is some like at the beginning there will be the formats are like well separated, then afterwards when you are reaching to the end, then the higher formats are moving towards the lower formats, yeah, right. And you can see for certain vowels, for example here in this case you can see only low frequency content is observed, not much high frequency content is observed. Whereas if you look at here also U, where only low frequency content is there and the remaining portions is almost like bright color or white in color. So, it means that the energy that is associated with the high frequency content is very insignificant. So, this may be true, you can able to visualize that when you try to utter the vowel U, where our vocal tract system like is observed to be like a uniform tube, right. And whereas for other vowels where the vocal tract shape is somewhat complex, so because of that you have the multiple resonances you can able to observe, where in case of U and some other vowel like O, where almost like vocal tract system is kind of rounded and then observed to be uniform tube. So, So, therefore, only single frequency resonant frequency was observed, right. So, these details you can, so from this it is clear that one can you can able to see a better discrimination from the spectrograms compared to the time domain waveforms. From time domain waveform you can see the periodic pattern, and if you see slightly more detail you can see a distinction you can because each of the waveform appears to be unique, but it is very difficult to directly identify or discriminate the vowels from the time domain signals in comparison with the spectrograms. Yeah, this plot corresponds to a plot corresponds to like F1, F2. It means here for every frame or from the vowel the spectral frequency, that means for every frame we will compute the, or otherwise for every vowel you compute the F1, F2, the mean F1 and F2, and then this F1 and F2 are plotted as a points, because you see this is a two dimensional plot, right, and x axis is the F1, that is formant frequency 1, and y axis is the formant frequency 2, and here this is a scatter plot. You can see there are points here, each point corresponds to like the mean F1 and mean F2, right, because here point means this point corresponds to like two coordinates or two values, one is corresponds to F1 x axis and other corresponds to F2. So, here there are lots of points, and all these each point corresponds to like a pair of F1 and F2, a pair of values F1 and F2, and here this plot all these points corresponds to. So, here from different people, like from a different from the gender, from both the genders male and female, from a different age groups, like these vowels have been collected from each of the person, 10 vowels have been collected, and then their spectrum has been computed, and from each vowel like they have computed the mean F1 and mean F2 and they have been plotted. So, likewise they have collected the vowels from a person, like a 10 different vowels from each person. Likewise they have collected from several people, and where from both male and female speakers, and the age varies from children to the aged people. So, if you look at a point corresponds to, it means suppose from a person 10 different vowels have been collected, it means 10 different points corresponds to a person are placed in this plot. Likewise from several people it has been collected, and then all their from each of the vowel segment the F1, F2 values are calculated. But how to calculate that? We will, as we had mentioned that from the spectrogram, like as a spectrogram, you take a vowel segment and then you compute the like the spectrum for each frame. Likewise from based on the length of the vowel segment, you have different frames used to be there. For every frame you will compute F1 and F2 and then take an average across all the frames, then we will get a pair of values F1 and F2. So, the pair of values corresponds to mean F1 and mean F2 corresponds to a specific vowel uttered by a particular speaker. So, that way for all speakers, for all the vowels, they calculated the mean F1 and F2 and it was plotted over here. Then from this, what you can able to observe here is that here suppose for example, if you plot the F1, F2 values corresponds to vowel U from several speakers, you can able to see that all those that F1, F2 values, they are different, they are spread over. If you look at here the vowel U, if you plot the F1, F2 values corresponds to the multiple speakers, you can able to see the values are spread over. They are not like all the values are not same. F1, F2 values for multiple speakers, it is not same, they vary. So, therefore, these here the ellipsis corresponds to the spread of F1, F2 values across the speakers, right. This is for the vowel U and this is for the vowel E, this is for the vowel E, like long vowel, this is for the vowel A, this is for the vowel A, likewise this is for the vowel U. So, therefore, whatever the 10 vowels, whatever we have seen in the previous slide in the form of spectrogram, for if you plot or if you observe the F1, F2 values from a multiple speakers, and if you plot them, you can able to see the variability of the F1, F2 values, right, across the speakers you can able to observe. But there is, but from this is, you can see that means there is some variation, but that variation is not a random one. The variation is not random. They are spread, but they are not very randomly or spread across the plot. It is not that way. If you see all the points of U, they are within this ellipse, and all the points of A, they are within this ellipse, right. Likewise, for every for each vowel, the points are spread within a certain limit or within certain range. So, that way from this, so this particular plot is nothing but plotting the F1, F2, mean F1 and F2 for a different vowels uttered by the multiple speakers. So, from this the observation is that the F1, F2 values are this formant values, there is some legal variation or there is some variation with respect to the speakers, because that is obvious, because they are uttered by, because these are produced from the human vocal tract system or a speech production system, and the speech production system for every individual is distinct, is different, because if you look at the speech production system or our oral cavity or nasal cavity and the dimensions or the geometry, so that will be distinct or that will be like vary from speaker to speaker, right. So, that because of that you can able to see the F1, F2 values also, they also vary slightly, they are also vary within certain limits, right. But at the same time, because of this variation only, you can able to perceive the vowels from a different speakers in a different way, but they, all of them you can interpret as the same sound unit, but you can able to see clearly the vowels that are uttered by different speakers are observed to be different, but we will interpret them as the same sound unit, because of that is because of the speaker characteristics or a speaker specific vocal tract geometry. So, you can see here these are there are 10 different vowels, and like they are mostly there is some overlapping is also there, and these overlap areas and all, they leads to confusion. If you go by, if you want to identify these vowels based on these formant frequencies by a machine, right, then these overlap areas and all, they leads to the erroneous values and all, because here at the overlap region we need to decide whether it belongs to U or O, right, and so there will leads to confusion or ambiguity, and with that leads to errors, erroneous. So, from this plot the observation is that the vowel sounds, for the vowel sounds, if you plot the F1, F2 values across the speakers, you can able to spread in the values of F1, F2, and because of that that's where the challenge, that's where the difficulty in identifying the vowels from the speech signals by a machine using these formant frequencies. They give you some, by looking at the spectrograms you can able to see some distinction, but again there will be some overlapping between the F1, F2 values across the vowels of different speakers. So, that leads to confusion, that leads to ambiguity, and that is where the challenge in identifying or determining the vowels more robustly by a machine and all. Yeah, this plot is just derived from the previous plot, and from the previous plot, just by using ellipses and all, it will be difficult to, suppose if you want to recognize the vowels using a machine, right, using a system, then one way is that actually from the waveforms you try to compute F1 and F2 values, mean F1 and F2 values, and try to see that, like you have to recognize based on that. So, one way to do that, instead of by from the ellipsis, if you take a single value or if you take a centroid of the ellipse as as a reference point corresponds to each vowel, right. So, that way in the previous slide, if you look at here, the points are spread over in this plane, and we know that the points whatever is there in this vowel, they corresponds to vowel U, and here the points that are corresponds to in this vowel, they corresponds to vowel E, and this is for the long E, A, and then A, then then various versions of the various vowel. And here instead of from this, if you take a centroid of the vowel, centroid of each ellipse, so that is that is a reference point with which you can able to by machine you can able to identify the given signal, speech signal, whether it's which vowel it belongs to. So here these points are nothing but the centroids of the ellipses that were observed in the previous plot. You can see here, and here from these centroids you can see there are 10 centroids here, 10 circles, small circles. So each of them corresponds to the centroid of the one of the ellipses, right? And here here we have plotted a triangle, and this is nothing but the corners of the triangles corresponds to the extreme values offered by the F1, F2, the extreme values offered by the F1, F2 in the plot. So if you look at the centroids here, you can see this particular one corner, this corresponds to the vowel U, where it offers the lowest F1 and F2 values, the lowest F1 and F2 values. Whereas for the vowel A, where you can able to see that it offers the maximum F1 value and the lower F2 value, where F2 is low. It is not the lowest, I can say, but it is a lower value. And here if you look at E, where F1 is the low and F2 is the maximum. You can see a maximum F2 value and F1 is the lowest one. You can see F1 is the lower one, it is close to around 300, whereas F2 is around 2300. So these extreme values, if you join them, and it is known to be the vowel triangle, and other vowels are at different locations around this particular triangle. And using these values, the reference values, one can able to from a machine you can able to automatically detect whether the given vowel segment belongs to R, E or U, something like that. So it is not 100% accurate, but you will get the accuracy of to a rate of around 60%, 70% and so on. Yeah, this is the table corresponds to different the vowels, right? Here E, A, and then A. So these are the different vowels in the English language, right? And these are the symbols that were given by the IPA. It's known to be International Phonetic Alphabet. So these symbols are they are uniform across the various languages. As I mentioned that, so there are distinct sound units across the language. There are altogether across the languages, if you observe, there may be around 60 sound units used to be there, and but in that 60 there are around 40-45 sound units, they are common across the several languages, and from one language to other language there are very few sound units. So that makes the number of sound units or the sound units that are present in a language will vary from one language to other language. So these are known to be the phonetic symbols, or the phonetic symbols, the unique way of representing the sound units, and they are common. They are for even the same symbols that are used in the context of even other languages also. That means here all these for this particular symbol indicates a specific sound, and that sound will be present in English as well as French or Spanish or in Indian languages also. So that way any distinct sound unit is labeled using this IPA symbol, right? They are known to be phones, right? They are known to be phones, and for these things in a graphium, that means in English language they are these alphabets are used to represent them, and whereas in other language the corresponding alphabets of that language is used. And now you can able to see that all these vowels how they are in the context of in the English language. For example, this is going to be beat, bit, beat, bit, bet, bat, but, hot, bought. So here for us the hot and bought, it appears to be like a similar, very similar, very close for when we speak. But the mother tongue, the people having the English as a mother tongue, the native English speaking people, they can able to utter these sounds very distinctly. But for us, since in our Indian context, since our mother tongue is like we are from India, so we don't have these two specific vowels, we have only a. So therefore we speak both hot and bought as same, like the vowel whatever that is present in hot and bought, we utter almost similar. But the native English speakers, they can able to show the difference between pronunciation of hot and bought, right, and then foot, boot, and then bird. So that way here for each of them, the vowels, whatever the 10 distinct vowels whatever is present here, so their context, their occurrence in these words, it will be observed from this, right. So for each word corresponds to a distinct vowel, and for that these are the frequencies, they are the formant frequencies that are observed, because these formant frequencies are observed from the previous plot whatever I mentioned. They were collected from several people where the age varies from like children to the aged people. From each person they are collected 10 different vowels, right, all these vowels in the form of maybe isolated vowels. So then they measured the frequency, and afterwards they have taken the average across all the people. Then these are the like the mean frequencies, mean F1, F2, F3 corresponds to the vowel E, and E likewise A, and so you can able to see that for the vowels E, and you can able to here, if you observe here the first vowels like front vowels, where the F1 and the difference between F1 and F2 is very large. F1 is very small and F2 is bit higher. And as you move on, like as the tongue hump move towards middle and going towards lower side, where you can able to see the difference between F1 and F2 is not much, very is less. You can see at the beginning the first 2-3 cases where the difference between F1 and F2 is high. You can see in the first case the difference between F1 and F2 is almost like 2000, then it is about 1800, then about 1300. So likewise, as you observe here, the difference between F1 and F2 will be lowered as the tongue hump is moving from the front side, from the front position towards back, right. And these are the mean frequencies that were computed from the vowel utterances uttered by the several people, and yeah, from these you can also synthesize by taking these formant frequencies, and if you synthesize the vowels, then you can able to perceive that it's you can able to discriminate the vowels, right, by using these particular formant frequencies. So we will see that how to synthesize the vowels in a later part. Yeah, now actually here now we will look at these acoustic phonetic characteristics or properties in the form of time and frequency domains for different sound units. So far we discussed about a broader groups, like at a sentence level we have seen both the time domain and frequency domain representation. Then afterwards at a vowels we have seen. Now we see the other groups of sound units. So before going to the other groups of sound units, we will see here the diphthongs first, because these diphthongs are also like they are complex vowels, because if you look at the I, ow, they are like it's a combination of two vowels. It's a combination of two vowels, but they are not the steady vowels. So like it starts with the particular sound, starts with the one vowel, and then it terminates with the other vowel. So these are not to be glide. That means for the production of this particular sound like I, here you can see this spectrogram corresponds to the diphthong I, and this spectrogram corresponds to the diphthong ow, and this is corresponds to A, and this is corresponds to E, I. So, these are the different diphthongs, because as I mentioned already, since as these diphthongs, there are, you can see there are 6 diphthongs are observed in English, whereas you do not see in our Indian context, in our Indian languages, we do not observe these 6 diphthongs. In our Indian context, we observe mostly only 2 diphthongs, like I and ow. I and ow. Because of lack of other diphthongs, we cannot pronounce the other diphthongs as clearly as the native English speakers. So, here you can see this is I, and this diphthong is nothing but a combination of A and E. So, therefore, you can able to see when it starts, when you are trying to utter I, because we know that we have to utter E also at later point, but the initial sound is A. So, therefore, you can able to see at the beginning you have the the formant structure corresponds to the A, where we have the distinct formants like at different frequencies, at a lower frequency than mid range and so on. So, therefore, because and later as it tries to reach to the E, so therefore, initially itself, because of that the formant structure of A is not clearly observed. You can see, but it is not as clearly as you can see in a steady vowel A, right. So, therefore, you can see here starts with a low frequency, and then the next vowel, the following vowel is E, because this I is a combination of A and E. So, therefore, immediately you can see here this formant is transition to the corresponding second formant of the E, right. So, if you look at here at the end, the formant structure corresponds to the vowel E, because it is a low frequency, and then the next highest frequency is more than 2000, and this is a kind of like for example, this is I, or this is in between I and we. So, that is the reason that we have a low frequency, and we have another formant was there at very higher frequency, and there is a middle formants are there, but they are not clearly visible here. You can see here from this plot there is a formant over here, formant over here, and formant is here, and formant here. So, there are 3 or 4 formats that corresponds to vowel A, right, and finally they end up with the vowel E. So, therefore, here the lower formant, and then next higher formant is around 2500, right, and whereas here you can see this is ow. So, it means here in case of ow, it is nothing but a combination of A and W. So, therefore, initially corresponds to vowel A. So, these are the 3 or 4 formats you can able to observe, but later as you see the terminating vowel or the following vowel is U, but for the U the formant structure will be U means it is like a uniform tube. So, only lower formant or only the low frequencies are observed. So, therefore, all these 4 distinct formats, so they will be again converged to a low frequency, and similarly the other cases also you can see here, there are like 3 or 4 formats, but finally they observed to be only 2, and here you can see it starts with U and then ends with E. At U means you have a low frequency content only possible, and then when you come to E, we have like the low frequency as well as high frequency. So, in across all the cases where all the diphthongs, they are actually glides. Glides means they are dynamic in nature. That means vocal tract is not in a steady shape. At the beginning, at the end, the vocal tract is somewhat steady in state at the very beginning and at the end of the complete unit, whereas in the middle, most or almost like 70-80% of the unit, the vocal tract is in the dynamic shape. It is in the dynamic form. That means it gradually changes and reaches to a final point. Like maybe at 10 to 15% of the initial point, it may be in a stable steady state, and again at the end also it may be reached to the final point and it is stable at 10 to 15%, and the remaining 70% of the time the vocal tract gradually changes from its initial vowel to the target vowel, right. Initial vowel is A and the target vowel is E. So, therefore, R to E, the vocal tract will transition from like R to E, and where R has 4 formats and where E has 2 formats, prominent formats. So, that way the vocal tract shape gradually changes from one sound unit to other sound unit, but there is no separation, right. So, that way these can be viewed as a single sound unit, even though their characteristics are observed to be a combination of two vowels in a very successive way without any separation, right. So, these are known to be diphthongs, or sometimes we may call it as a syllable is nothing but more than one sound unit. The presence of more than one sound unit can be viewed as a syllable. After covering the diphthongs, the next group of sound units what we observed here in the previous class will be actually it is the semi-vowels, but here we are not discussing much about semi-vowels because the semi-vowels are also dynamic in nature. So, they are also dynamic in nature because you do not see any steady portion in uttering the semi-vowels like ya. So, all these semi-vowels they mainly depends upon its context, that means based on the next vowel or based on the next sound unit. So, most of its characteristics are influenced by the following sound unit, and so they are known to be like mostly the characteristics are transitional in nature, or like they are also kind of a gliding nature and all, and so therefore, from the waveforms it is difficult to see a specific characteristics of the semi vowels. So, therefore, here we are not showing. So, but here now we after the semi vowels, the next group of sound units that we are going to discuss over here is the nasal sounds, and you know that how the nasal sounds are produced. We discussed when you are discussing the speech production, we have seen how the nasal sounds are produced, right. So, nasal sounds are produced during exhalation process, and for the production of nasal sounds the vocal folds will vibrate. But here as you see these are nasal sounds, it means the speech production or the speech the vibrations or acoustic pressure variations. So, they are released from the nostrils, nasal cavity, not from the oral cavity. That way these are known to be the nasal sounds. So, for doing that, for production of sounds through nasal cavity, it means that the oral cavity has to be completely closed for during the production of these sound units, and here the examples of these sound units are like m, na, ma, na, na, n. So, these are the sounds which are produced through the nasals, and here as I mentioned that for the production of these sounds the velum will be lowered. So, therefore, the excitation is coupled to the nasal cavity and as well as the oral cavity, but the oral cavity is blocked at different places. So, depending upon the place of closure of the oral cavity, the corresponding nasal sound can be observed. For example, if you want to produce m, there the oral cavity is closed at lips, that means through lips the oral cavity is completely closed, but the excitation is coupled to both oral cavity as well as nasal cavity, and since the oral cavity is closed, so there will not be any emission of resonances from the oral cavity, but the nasal cavity whatever the excitation is coupled, whatever the resonances that are produced by nasal cavity, so they will emit through the nostrils. So, that way these the nasals you can able to see that the signal is observed to be periodic. And here for plotting these time domain signals of nasals, instead of plotting the isolated sounds, here they were plotted in between the two vowels, because generation of these nasals or any other later part the consonants and they are very smaller duration, it is difficult to it's difficult to observe their characteristics in its isolation. So, therefore, here for showing the characteristics we created a nonsense word by keeping different vowels at the beginning and vowel at the end. So, that way we will form a nonsense word, and then those nonsense words are recorded, and from that we will try to find out the waveform that is corresponds to the required sound unit and all. So, here in this case for the observing the characteristics of ma and na, where the sounds are the ma and na nasals, they are placed in between the two sounds like a and a, like you say emma, emma, and like enna, enna. So, if you record that, then you can say that the initial portion of the periodic portion with a higher amplitude, this corresponds to the vowel A, and similarly at the end the higher amplitude, the periodic portion or periodic signal, this corresponds to the vowel A, and in the middle whatever the signal that was there, this is corresponds to the nasal, this is corresponds to that particular sound, nasal sound M. And similarly in case of Na also, you can see the same vowels are appended at the beginning and later. So, when you if you want to capture the signal nasal, here will append will form a word where a vowel kept at the beginning and vowel kept at the ending, and will try to utter, if you try to record that ena, and then if you plot that, you can able to see that a beginning of a periodic pattern corresponds to vowel A, and at the end the periodic pattern corresponds to A. In between whatever the signal is there, this is corresponds to like N, Na, Na. And here if you observe both M and Na, you can able to see that almost the time domain signal remains same, almost equal, almost similar, very similar. You cannot make out which is M and Na, both are appears to be similar, because the reason is that you can see both of them, for both M and Na, the signal, the speech signal that is released through the nostrils, that means the entire nasal cavity is contributing that. So, for both of them the same nasal cavity is contributing, but the only difference is that where the oral cavity is blocked or where the oral cavity is closed. In case of Ma, the oral cavity is closed at lips. So, with that this total the oral cavity and the nasal cavity that contributes to Ma, whereas in case of Na, where the oral cavity is closed at the teeth and the remaining portion of the oral cavity and the nasal cavity is contributes to the vowel Na. And here in the whatever the excitation that is coupled to the nasal cavity, so that will be released through nasal nostrils, and whatever the excitation that was coupled to the oral cavity, so there based on the shape of the oral cavity some resonances are produced, but they are not emitted. So, they will be observed through these muscles that are there in the oral cavity, and so those resonances that are produced by the oral cavity, and those are known to be anti-resonances because they are not emitted. So, they will be absorbed by the muscles, by the muscles of the oral cavity. So, they are absorbed, that means the energy that is due to that resonances, they are not emitted, they are not as part of the acoustic vibrations of the speech signal, they are like absorbed by the these things, and you can able to observe very low frequency corresponds to that. So, these are known to be anti-resonances because the resonances are produced, but those resonances are not emitted into the air as part of a speech production. So, these are known to be anti-resonances and all. That means they are like die down, the resonances are produced, but that energy will be like absorbed by these oral cavity and all. They are completely absorbed by the oral cavity, therefore, they are known to be anti-resonances. Whatever the resonances that are produced by oral cavity, they are simply die down, they are like absorbed, right. Whereas the nasal cavity, whatever the resonances that are produced, they will be emitted through nostrils, so that you can able to observe in the spectrogram and all. And because of that, actually can able to see in case of Ma and Na, the only difference is that the anti-resonances whatever is present in the signal, they are different, because in case of a Ma, where the entire oral cavity contributes to the anti-resonance, the entire shape of the oral cavity Ma, because till lips you have the like the oral cavity, whatever the excitation coupled, it will come till lips, and this entire thing, the oral cavity acts as the anti-resonance cavity, or the resonances whatever produced, all of them are absorbed by our these muscles, you know, at the glottis and around the jaws and so on. Whereas in case of Na, where in the oral cavity only it is blocked at the teeth. So, therefore, the size of the oral cavity is less in case of Na compared to Ma. So, that makes the difference between the anti-resonances that are produced, and with that one can able to discriminate the Ma and Na. Otherwise, the distinction of Ma and Na is very difficult from the by using either time domain signal or by using a frequency domain also. It is very difficult to discriminate Ma and Na by a machine, because the machine will extract the information from the time domain signal or frequency domain signal, right. In the time domain signal, both signals appears to be similar. You can see here this one, the waveform, the fluctuation of waveform, amplitude, both appears to be very similar, right. So, therefore, from a machine we do not what are the features that are extracted here from Ma, and the same thing is observed at Na also. So, you can able to say that it is a nasal, but which nasal is the discriminating between the nasals is very tough or very difficult using a time domain properties of a signal. So, let us see the corresponding frequency domain. So, in the frequency domain also, if you look at here, so this is the time domain plot, the bottom one, like this is for Ma and this is for Na, and here if you see that in this Ma, the Ma portion is this one, because this is the vowel corresponds to A and this is the vowel corresponds to A. In between the Ma is there, Ema. So, in this Ema, so this small portion corresponds to A. You can see clearly the slightly higher amplitude, and here also we have much higher amplitude Ena, and whatever the lower amplitude that is there in between these two distinct periodic pattern. So, this corresponds to the nasal, time domain waveform of a nasal, and here also this is corresponds to a nasal Na, N corresponds to time domain waveform. And if you look at here their corresponding spectra here, both of them you can see very low frequency, because here the resonance is due to the nostrils, and where the nostril, where the nostril cavity, there is no other articulator to block that. The whatever is coupled based on the shape of the nasal cavity, the entire nasal cavity will offer a resonance. So, that will be low frequency content, So, therefore, you can able to see that in both for Ma and Na, the low frequency, that means the energy is concentrated at a low frequency. You do not see much higher frequency. Here you can see a slight trace of that, but other than that most of the energy is focused at the concentrated at the low frequency end only. So, from the spectrogram also you cannot discriminate that whether it is a Ma or Na, right. So, the only way to discriminate that is that if you can able to identify the anti-resonance, if we can able to identify the location of the anti-resonance, it is nothing but the frequency of the anti-resonance, then that is distinct, that is distinct between Ma and Na, because in case of a Ma, the anti-resonance is offered by the complete oral cavity, that means from the lips to till the velum, right, the entire thing acts as a resonator, and that whatever the energy that was, whatever the resonances that are contributed, that will be absorbed completely. Whereas in case of Na, where the oral cavity, the size or the shape of the oral cavity or the volume that is offered by oral cavity in case of production of Na is different from production of Ma. So, that way based on somehow if you can able to analyze the anti-resonances, and based on that one can able to discriminate the nasals Ma, Na and the others also, because only the Ma and Na are present prominently in English, whereas in our Sanskrit and Indian languages where you have other sounds also, like Na is also there, Na is there. So, there are 4 or 5 nasals that can be clearly observed in Sanskrit and our Indian languages and all. So, for all of them you can able to see, if you want to identify, if you want to discriminate them. So, using proper resonances you cannot discriminate that, because for all of them the resonances are offered by nasal cavity, it is a fixed shape, right. So, the only way they can able to discriminate it will be based on the anti-resonances, because the anti-resonances are offered by the different sounds, different nasals will be different because of the closure of that the oral cavity at different positions. So, therefore, accordingly you have anti-resonances are different. So, that way the nasal sound units, if you want to discriminate the nasal sound units based on directly the spectral properties or time domain properties is very difficult, it is highly ambiguous. So, the only way to like discriminate these is based on the anti-resonances, or you can say that in the later on we will discuss that is known to be zeros of the system and all. Like you can say that the poles means like formants and are the resonant frequencies, and the zeros means like anti-resonances, because the frequencies are resonated, but that entire energy will be trapped in the oral cavity itself. It is not emitted at all, it is completely absorbed by the muscles and is completely trapped by the oral cavity. So, there based on the size of the oral cavity, you have the different resonant frequencies, and that way they are can be viewed as the anti-resonances. Yeah. Then we move on to the next group of sound units. They are known to be fricatives, and here again there are two types of fricatives: voiced fricatives and unvoiced fricatives. So, we know that the fricatives are produced due to the presence of narrow constriction in the oral cavity at different positions, right. And here the example of the three fricatives, three unvoiced fricatives were shown here, like one is fa, sa, sha, and if you try to visualize that, the fa is a fricative that is produced, all three are unvoiced fricatives. It means for the production of these fricatives, the vocal folds won't vibrate at all, the vocal folds will completely open, and the excitation is because of the constriction in the oral cavity at some position. But here the constriction is not complete. Here the closure is not constriction is not complete. The constriction is like a partial. It's almost like tries to close the vocal tract, but it will not close completely. There is some narrow opening will be there. So, with that the air will be rushed, and the turbulence acts like the excitation, right. In case of fa, where you have a narrow slit or narrow opening at the lips, the lips tries to close that, but for the production of fa, where there is a slight opening of the lips, the lower lip with the upper lip. So, that gives you the excitation that produces the sound unit fa, right. And here also, like again sa, where at the teeth are slightly behind the teeth, you have a narrow opening. So, with that the air will be rushed, and then the frontal portion acts like a resonator, and the back of that acts like again anti-resonator, because whatever the volume that was there at the back of that excitation point, that acts like the anti-resonator, and the frontal portion, because the excitation starts and then the air will be rushed through that. So, the front portion, the frontal volume, like in case of sa, where the position of the narrow opening will be just at the teeth, at the retroflex, at the teeth, right, behind the teeth, and the frontal portion from teeth to the lips. So, that small area, the small volume, so that acts as a cavity, frontal cavity, that acts as that produces a corresponding resonances and all, right. And at the bottom, at the back side, that acts as that is also a resonator, but that also creates resonances, but those will be trapped behind, they will not be emitted, right. So, that way if you try to analyze fa, sa, sha, where you have that narrow opening at different positions, starting from lips to the teeth and then back of the teeth, much back, like a palatal or somewhere sha, right. The tongue hump also will be there. So, therefore, all those the manifestations, the results to a different sound unit. You can see in case of fa, there is like fa, where you can able to see the signal strength is not much, therefore, you may not hear, you are not noticing much noise or much turbulence over here. And whereas for sa, you can see some kind of a random fluctuation or random turbulence you can able to see here. Whereas in case of sha, where you can able to see the more pronounced the random fluctuations in the signal and all. And here also for the same way, like since you cannot observe the characteristics properly when you speak these sounds in isolated manner. So, therefore, these fricatives also, they will be placed in between the two vowels, and that forms a word, right, and that word will be uttered, like here fa, where a is the vowel and then a is also vowel. So, from these time domain waveforms you can able to see this is corresponds to the periodic, the initial periodic structure corresponds to the vowel a, and the last part corresponds to the periodic structure a, and in between whatever is there, that is time domain signal corresponds to a fricative fa, and here sa, and here sha, right. And here you can see these are the respective spectrograms. You can see here, this is the time domain signals, right. The same thing like FA, SA, SHA, right, and their respective spectrograms here. And in case of Fa, you can see that the signal strength of this frication is very small, very less. So, therefore, you do not see there is some noisy pattern, or you can say that some high frequency like content is observed, but it is not much, right. So, that same thing that also can be observed in the time domain, and whereas in case of SA, this is slightly more stronger compared to here, the noise effect of noise. Noise means it is like high frequency content where the energy is focused in the high frequency region, and there is no structure at all. Here this entire all these frequencies have the energy at this range around 3000 to 4000, and at low frequency you do not observe any energy at all. And whereas if you see the SHA, where you can see more darker cloud or darker region at a very high frequency, right, and at a low frequency anyway there is no signal, there is no frequency content. It means that the frequencies they are present, but they are insignificant energy, but the high frequency content has more dominant energy. So, that you can able to perceive in a fricatives like unvoiced fricatives, where you can see that as you move like frication from the lips, where you can see that the energy is less, and then the SA, it has more energy compared to the frontal fricative, and SHA has much more significant energy that is observed at the high frequency range. And you can also see the corresponding time domain signal also, the corresponding the random fluctuations over here. And here for all of them you can see that there is no periodic structure, but if you look at here, because to indicate, to show that only here the vowels are used at both ends, where you can see a periodic structure here, and the same periodic structure is also observed in the spectrograms as the vertical striations. But whereas here in the noisy portions you do not observe any striations and all, right. So, because since they are the unvoiced fricatives, and you see that now these are the, now here again the counterpart of unvoiced fricatives are the voiced fricatives. Like here the example, there are two voiced fricatives were given, va and za, va and za, and likewise here in the previous case, where in the previous slide there are three sounds are given corresponds to unvoiced fricatives like fa, sa, sha, and similar to that in case of their voiced counterparts are va, za, ja, va, za, ja, right. So, these are the voiced fricatives. So, the same way here these voiced fricatives are recorded, like keeping the vowel at the front and later part of the voiced fricative, like you say eva and eza, and so by keeping the fricatives in between, and then you record the word, it's a nonsense word because it does not have any meaning, and this is for the analysis purpose. We recorded the voiced or unvoiced fricatives between the two vowels, right. Not only even the other sound units also, we have seen even the nasals also, we kept a nasal in between the two vowels and then recorded that, and we observed that how the time domain characteristics are and what will be its spectral characteristics. Here if you see, since it is a voiced fricative, it means here you can see there is a narrow opening will be there, air will be rushed through that gives you a frication, and during the process the vocal folds also vibrate. So, because of that you can able to see a periodic structure in the frication region. There is a frication where you can see a periodic structure here, right, and here the periodic structure at the beginning with a higher amplitude, this corresponds to vowel, and again a periodic structure at the end with higher amplitude, this corresponds to again another vowel. In between you have a periodic structure with very low amplitude, this corresponds to frication, va, like voice frication. It means there is a narrow opening, with that the air will be rushed, and during the process the vocal folds also vibrate. So, because of that you can able to see a periodic signal as part of frication. And similarly the other case, in case of eza also you can see a frication, and along with that you can also perceive some kind of a turbulence. Because of that, along with the voicing, along with the periodic structure, you can also see some kind of a noise also associated with that in case of Ezza, Ijja also, right. So, that way these are the voiced fricatives, and here the voiced fricatives and unvoiced fricatives, their production mechanism, for both of them, their production mechanism is same, exactly same. The only difference is that in case of voiced fricatives, the vocal folds will vibrate along with the frication, whereas in case of unvoiced fricatives, vocal folds remains open, there is no vibration of vocal folds. So, that is the difference between voiced fricatives and unvoiced fricatives. So, these are the time domain waveforms corresponds to voiced fricatives. In the next class, we will discuss about how the spectrograms or frequency domain characteristics of these voiced fricatives, and then we will move on to discuss about the other groups of sound units like sound stops and voice stops, unvoiced stops, and so on.
In view of speech production, so far we have discussed in the theory about how the various speech sounds are produced with the help of the excitation source and the vocal tract system. And here, for better understanding of the speech production mechanism, so there are animations that are available at the YouTube created, they are available in the YouTube, and you can able to visit these following links, and where you can able to see the animations related to the production of different sound units. So, here you can able to clearly visualize how the various speech sounds are produced, like the vowels, consonants, and again in the consonants there are different types of consonants like voiced stops, unvoiced stops, nasal stops, fricatives. Likewise, each of the sound unit, how they are produced, like for the production of each sound unit. So, what is the excitation source and how it is coupled to the either oral cavity or a nasal cavity, and what are the various articulators that are that are part of the production of the particular sound unit. So, all those things you can able to clearly visualized by in these animations and all. So, in view of that, I recommend to follow these, go through these links, and you can able to see the animation videos. So, with that you can get a better picture of picture and understanding about the speech production, particularly to different categories of sound units.
We will discuss about the spectrograms corresponds to these voiced fricatives, and after covering that we will also discuss about acoustic phonetic characteristics of stops. Okay.